You can engineer robust back-end logic, structure pristine data pipelines, and deploy flawless front-end code. But in modern web development, all of that infrastructure carries zero value if a search engine cannot index and present the final data to the user. We are going to trace the exact engineering lifecycle required to solve this delivery paradox, following a 5-tier visa classification system as it is deployed across a database of over 23,000 job listings. This split-screen comparison shows the two ends of the pipeline. On the left, raw database records contain accurate visa information, but are invisible to the public. On the right, a highly ranked Google-rich snippet parses and displays that exact data. Connecting those two states requires a specific architectural journey. We start at the bottom, executing idempotent migrations on the database, and build upward through structured data generation, route handling, and programmatic front-end SEO infrastructure. Full-stack feature delivery operates as an unbroken chain. Generating data is only half the equation. The feature remains useless until you engineer its exposure. The first technical hurdle sits at the database level. Before the front end can display visa classifications, we must run a migration against a live production environment and apply new classification tags without causing downtime. Safe, repeatable execution requires idempotency. By constructing every SQL statement with an if not exists clause, the pipeline ensures that if a network interruption forces the migration to run twice, it will not overwrite or corrupt the live tables. Once the schema is updated, the system faces a scale constraint. There are 23,000 existing job records that need classification. Attempting to process ease row by row would tie up server resources and bottleneck the database with excessive write locks. This diagram illustrates the batching solution. Instead of thousands of individual transactions, the pipeline collects job IDs in controlled batches of 1,000, specifically targeting rows where the classification column is null, ensuring computing power is spent only on unprocessed records. But that initial backfill leaves an edge case. Thousands of job descriptions contain no explicit mention of visa sponsorship, leaving them classified as no data. To resolve this ambiguity, we introduce a fifth inference tier. If the job description is silent, the system looks at the employer's historical behavior to deduce whether the company is historically sponsor-friendly. Look at how this join operation merges the current jobs table with a dedicated company sponsorship table, filtering for active H-1B records. This batch update is overwrite safe, targeting the no data subset, so definitive tags are never overwritten by company history inference. Back-end processing is the prerequisite to visibility. We have to successfully transform inert rows into actionable, classified signals before any front-end routing can begin. With the database populated, the engineering focus shifts upward to the Next.js front-end exposure layer. Simply rendering these job listings as standard HTML is insufficient. Specialized search surfaces like Google for Jobs bypass standard text crawling and look for strictly formatted structured data. This wireframe demonstrates mapping front-end fields directly into a valid JSON LD job posting object. Missing mandatory fields like title or date causes crawler rejection. We apply layered regex for locations, using explicit telecommute tags for remote roles to keep the JSON valid. Generating the data is only part of the front-end equation. We also have to engineer defensive crawling rules to protect the domain's search reputation. A severe duplicate content risk arises when a site architecture allows users to view job listings in both modal overlays and on dedicated standalone pages. Crawlers view these as two competing URLs for the exact same content. To resolve this, Next.js metadata generation rules enforce a strict canonical URL pointing only to the standalone page. Furthermore, expired job listings are tagged with explicit no-index directives. By integrating structured data defensively, we ensure search engines only consume and reward the most accurate, live information available on the server. Even with perfect metadata, there is a mathematical limit to discoverability. Relying on a crawler to naturally follow standard links to discover 23,000 isolated job pages will result in gaps in the index. To guarantee discovery, we build dynamic route handlers in Next.js. These route handlers generate the required application/XML response in real time, executing logic on the server to present fresh data to the crawler. This sitemap tree navigates Google's 50,000 URL limit per file. A root index directs crawlers to distinct sub-site maps for jobs, companies, and static pages. Approaching the threshold, a sharding mechanism automatically splits the job sitemap into multiple sequential XML files. This architecture manages a finite resource known as the crawler budget. Search engines will only spend a specific amount of computing time on a single domain before moving on. To maximize that budget, the sitemap's underlying SQL query must align directly with the front-end indexing rules. By adding a strict filter to the database query, the sitemap ensures it only returns currently active job listings. Feeding dead or expired links to Googlebot carries a technical penalty. It forces the crawler to waste its allotted budget on blank pages, which degrades the domain's authority and slows the indexing of fresh content. For large applications, the sitemap operates as an optimized database query designed to manage the crawl algorithm's attention. With the individual listings indexed, the strategy shifts toward programmatic SEO, engineering pages to capture high-intent, long-tail search queries. A generic job board homepage cannot organically compete for highly specific user searches, such as H-1B jobs in Seattle or OPT-friendly developer roles. This generation matrix maps 30 U.S. tech hubs against 15 target engineering roles, outputting a footprint of hyper-specific URLs. This constants matrix feeds a single Next.js template, where the server programmatically spins out distinct static routes without manual page creation. By leveraging static parameter generation and incremental static regeneration, these pages build themselves at request time and then automatically fetch updated database counts in the background. But deploying hundreds of auto-generated pages introduces a risk. If Google determines the pages look identical, it applies an algorithmic penalty for templated duplicate content, burying the domain in search results. To ensure uniqueness, the template receives live database statistics alongside a tailored FAQ object. Passing city and role parameters generates distinct questions, answers, and a unique FAQ page JSON LD payload into the page headers for every route. This targeted variation ensures no two programmatic pages are identical. It forces the search algorithm to treat each generated route as highly relevant, distinct content, making it eligible for rich snippets in search results. Successful programmatic SEO relies on engineering distinct, data-backed value into every automated render, validating the pages to the search engine. With the codebase fully deployed, we arrive at the final validation layer, Google Search Console. Shipping complex back-end logic and front-end schemas achieves the objective only if the end platform successfully ingests and validates the data. This initiates a final remediation loop. The system tracks coverage warnings, resolves missing recommended fields, and adjusts JSON LD fallbacks to ensure every algorithmic flag clears. This completes the system's activation. Back-end SQL and front-end metadata are exposed to the web, responding directly to search queries through the live index. The measurable outcomes reflect the precision of the pipeline. The generated pages achieve top-tier Lighthouse SEO scores, and thousands of previously excluded URLs are pushed cleanly into the live search index. Successfully delivering a data-driven feature demands an unbroken engineering chain. It spans from the first idempotent SQL command in the database directly through to the final metadata tag parsed by the crawler. In modern web applications, architecting the discoverability of the data is just as complex and just as critical as engineering the data itself.